So talking about these quadratic equations, quadratic functions, if you will. So second degree equations, and what does that mean? Second degree function, what is that? We've hit the wall already? What does it mean to be second degree polynomial? Yes, we learned this. Yeah, we did. It was a while ago. So let's see, how do you find the degree of a polynomial? First of all, is this a polynomial?
Degree.
I don't know what this means, but I have to make this stuff up here. Okay, is this a polynomial? No?
One? Yes.
What makes it a polynomial? How do I know it's a polynomial? Is this a polynomial?
No. No.
Why not?
Because it has a fraction.
Well, how about this one? That a polynomial?
Yeah.
Yes. This is a no, this is a yes.
Because the x is in the fraction.
X is in the fraction. Remember how you can rewrite this as x to the minus 1 plus 5? Remember that?
No.
No? Really? Negative exponents. Okay. Things to brush up over the summer. Negative exponent is this 1 over x. You must have positive, you can have 0. So 0 or positive exponents to be a polynomial, and all these do. So it means you can't have variables in denominators. You're adding and subtracting those things, right? So products of numbers or variables and numbers. So how do I know what the degree of a particular term is? Like what's the degree of this particular term? What's the degree of 3x to the 5th power? Huh? 5? How do you know what it is? Because it says 5 right here, right? It's basically how many variables. There are 5 x's here. X times x times x, right? So this has a degree of 5. What does this have a degree of? 2. X times y, you're multiplying 2 variables twice, right? 2. What's the degree of this one? 2. What's the degree of this one? And what if I would have had plus xy squared z4? What's the degree of that?
7.
1 here, 2 here, that's 3 variables. You got 4 more variables, that's 7. Now what would the degree of the entire polynomial be? 7. Biggest one wins. So it's, yeah. Okay, so that's the degree of a polynomial. So if I have a second degree polynomial, what's the most number of exponents that can be multiplied, or variables that can be multiplied together? 2 of them. So a second degree polynomial, an example would be, I don't know, y equals ax squared plus bx plus c. What is the degree of this polynomial here? This one's 2, this one's 1. What about a constant? What's the degree of a constant term? 0, right? I don't have any variables that I can see here. So they look like this. That's quadratic, okay? Real world applications, a whole bunch. If you look at the shape of a cable on a bridge, that is a parabolic shape, quadratic. Area is very quadratic because you multiply like an x times a y. So it's going to be a second degree. Trajectories. So you fire a cannon, right? That path is quadratic. Falling objects, yeah, they do have a quadratic path to them. Path of orbital objects, that's, path like this is quadratic. And then the most famous one of all, these golden arches, each one of them quadratic. You couldn't have McDonald's. Well, I guess this is not the quadratic's greatest moment. But yeah. So anyway, quadratics. And what they are conic sections. Conic section. Section just means a cut. So you take 2 ice cream cones and you put the points together and you cut a slice through them. So here's our friend the parabola. When you cut that way, there's where they come from. We learned about circles this year, right? And then when you're in pre-calculus, I think they do these now. The ellipse is when you cut this way, it's a squishy circle, an oval shape. And then the hyperbola, which if you remember inverse variation, remember inverse variation?
Yeah.
Remember this? Anybody?
Yeah.
Right? That thing they look kind of like this. That's a hyperbola. That's this when you slice through this way. So conic sections are kind of an interesting thing in math. So did them this year with this one. Last year we did that, and you'll do it some more next year. And these you tend to see more in a pre-calculus type class. Alrighty. So let's review. This was kind of some of the questions that came up during the warm-up. And we did a lot of this review already, so we should remember it. So here is a parabola. The vertex axis of symmetry. So here's the standard form, and I really should put like f of x equals this. So it's a function I'm talking about now. Ax squared plus bx plus c gives you y values, and then you get this kind of shape. This is my parent function, y equals x squared. Next class, we will be working a lot with this idea of a parent function. So it's kind of just a generalized version of it. The vertex, we talked about this, it's the lowest or highest point. It's the turning point. This one here, is this a maximum or a minimum? It is a minimum value. And by minimum value, we mean the minimum y value that this function will have. The domain is all real numbers as shown here, but the range is all y's bigger than 0. Isn't it? Isn't this the range? Remember set filter notation? Remember that? Yeah. What's the domain? What are all valid inputs that I can put in here? What about x? All x's, all real numbers, right? All real numbers is my domain, right? I can put an x in over here, negative 4,000. If I go up high enough, there'll be a y value, right? So how do you write that in set builder notation? One way is this. All x that are real numbers, element of the real such that x is in the set. Remember, I'm just trying to refresh the memory. Is it working?
Yeah.
Okay. And again, the axis of symmetry, we know about lines of symmetry because we've just taken geometry. So it splits it. It's like this is a reflection of that. All right, good. Parabolas or concavity. We did talk about this last time. Parabola opens up. That's the smile shape. That's this. We also can have concave down. That's when it's a frowny face. Looks like that, right? And I'm just going to put up here just what our general form is, standard form of a parabola function. So if a, this leading coefficient, is a positive number, then it will be this, a concave up. And if it's negative, it will be a frowny face. You will have a minimum and you will have a maximum value. What else? So if you have your graphing calculator, it's a nice kind of idea to really get a good feel for what these shapes are. So if you have one, I hope you do, go ahead and just put in press y equal, in case you forgot how to work all this. Remember where x is? If you look at the alpha button and look one to the right, there's where x is. And then you hit the square button. Yeah? We know where that is. And then we hit the graph button. Right there's y equals x squared. If you want to see what y equals negative x squared looks like, I'm going to put it as a y2 so I can graph them both. Careful to use negative instead of the minus sign. Again, x squared, here it is. And so the first thing I'll see will be x squared, and the second thing will be negative x squared. So here's negative x squared. So what happened there? What happened? What are the new words we learned in geometry about this thing and this thing? It's a reflection across what? The x-axis. So here's our parent function. I put a negative in front, and I get a reflection across the x-axis. So again, these transformations can be very helpful when graphing. Yeah, we'll be more detail on that coming up soon.
Can you make it so simple?
A little harder to do on this because his question was, can I make it look like this? It's a little bit hard to do on our graphing calculator because our graphing calculator graphs functions. Caleb, is this a function? No, why not? Well, pencil, what about the pencil? The pencil test, right? You have a pencil, you hold it vertical, and remember that functions, every input has one and only one output. So look at this input here, this x. It's got an output up here, and it's got an output down there. There is more than one output for this input. It is not a function. It can be graphed on our calculator, but it requires a couple of tricks. So, generally speaking, hard to do on our calculators, but not impossible. All right, continuing. We use these transformations on our parabolas. Now, I'm talking about dilations here. We're more familiar with those than when you saw this last year, and I hope you did see this last year. What does this notation mean here? I just want to remind us what A is. What are these little bars called? absolute value. What does it mean by absolute value of A is bigger than 1? Yes, sir. Yeah. So what is this trying to tell me here? If the absolute value of A, if the magnitude of A is bigger than 1, these properties will be true. So, so if I have like negative 2x squared plus bx plus c, whatever it is the magnitude of A bigger than 1 here? Yes. Even though negative 2 is not bigger than 1, I'm only interested now in the 2. So if this number over here, without the sign, is bigger than 1, I get a very narrow parabola. It's a stretch. It's a dilation where I stretch it. Now, if the absolute value of A is less than 1, well, what range of values am I talking about here? I'm talking about x's between negative 1 and 1. Are we familiar with this notation?
Yes.
It says x is bigger than negative 1 and x is less than 1. So it is between negative 1 and 1, but does not include negative 1 and 1. If that is the case, I get what we call like a compression. We get wider. So if you see like a 2x squared, I expect to be kind of a skinny looking one. And if you have a half x squared, I expect it to be a little bit flatter. But a little bit flatter or narrower than what? Our parent function of y equals x squared. So to play around just with the calculator a little bit more here, if I were to turn this instead of x squared, I want to turn it into 4x squared. See if I did that right. And then for now, we'll just get rid of this one. I'm going to put my x squared back. I'm going to take that back. I'm going to put x squared back. Because I want you to see the parent function. So the first thing is 4x squared. The second one is x squared. So here comes 4x squared. And here comes x squared. So this is my parent. That's what they normally look like. But if you put a number bigger than 1 in front of that x, it gets skinnier. It's like you pulled on the strings and pulled it tight. Now what happens if you put a number in between negative 1 and 1? Well, let's find out. So the way you type in a fraction here is don't convert it to a decimal. Just put it in parentheses. 1 divided by 4, close parentheses, then put in your x squared. So I'm going to see 4x squared, I'm going to see x squared. Last thing to graph will be this 1/4 x squared. It is kind of a flatter one. It's a compression. It's like you're pushing down on it. So the relationship between A has a couple of things, right? So if A is positive, concave up, and if its magnitude is bigger than 1, you get a skinnier curve than you would from the parent function of x squared. If the A is between negative 1 and 1, its magnitude is less than 1, then it becomes a fatter one than your parent function of y equals x squared. What's going to happen if I put a negative in front of each of these? It will go down. You get that reflection. So knowing transformations is actually very helpful when you're trying to graph these kinds of things. As we'll see next time. I can't wait to do that part. It's fun. Okay, but let's do, again, I'm going to review this. We did this last class, but this is our formal notes. You can write all this down here. It's on the bottom of page 1. I want to graph or sketch. Sketch means, I know it's not going to be perfect. I'm just going to find some key points to kind of guide what it's going to look like. F of x is x squared minus 6x plus 5. Bottom of the page, so you write it down. Okay, so a couple ways to do these manually is, one way is the table of values, and I don't want to discount that. And then we also have using properties, which is what we reviewed a little bit last time. There is, of course, the graphing calculator. Why is it important? Like, if you have this thing here, why do we bother learning how to do this by hand? Why do we waste our time with this? Why? Yes. You have like a parabola emergency. You need to graph it. No calculator. What are you going to do? Right? So you know how to do it manually. Excellent. You don't have a calculator. What would be another reason why it's important that you have a calculator? And very often I use this to verify I did it right. Why is this kind of important? Why is it important to just kind of be able to do this by hand? I can ask the same question. Why do we even learn like multiplication tables if we have calculators? Why do we bother doing that? That's another good question. It's a topic of debate, isn't it? Why do we bother like making, when you're in second or third grade, you have memorized those tables? But you love that, right? Now, why do we make you do that if you have calculators? They're in everything, right? You know, people have little devices. They can just type it in. How come? It can be faster than typing it in, absolutely. Also, did you ever like type something and then say a hard one? I don't know, 267 times 42, and then you get Negative 4,619, like, or you get some wacky number. Anybody ever get that? You're typing something in the calculator. Yeah, don't you know it's crazy right away? You have a sense. It's called number sense, right? You have a sense of about what it should be. And so we want the same thing. When you're graphing something like this, you want a sense of what does this thing look like before you even put it in the calculator, so that you know you can make a mistake with data input. You know, it happens. So it's getting a sense for what are these curves, what do they feel like? And that is why we spend time doing this now, even though you can just do this. I mean, absolutely you can. And as you get higher up in math, simple things, you will just use this. But you have that sense in your brain now. I don't remember what's here. Oh, okay. Graphing this thing. What's table of values? Yeah, okay, never mind. Table of values, what is that? This is actually a very handy little tool. You've done this before when we did linear equations, right? And all you do is you say, well, let me take some members of the domain. Now, if it doesn't say, I'm going to assume the domain is all real numbers. So pick anything from the all real number set. And, you know, this is what we use with linear. We could use that here as well. And now you've got to plug these in. You know, okay, zero's easy, right? Let's plug in 0. What do you get? 0, 0, right? 5. Okay, so I know 1 point already. 0, 1, 2, 3, 4, 5. Now I'm just using table of values to show you how this works. So you don't have to necessarily graph this one. I would save the graph for the next one we're going to do. How about 1? 1's kind of easy too. 1 minus 6, right, is negative 5 plus 5. 0. Huh. Let's do negative 1. That was kind of easy too. Negative 1 squared is what? 1. Negative 1 times negative 1. Minus 6 times negative 1, that's a plus 6 plus 5. What's that? 12. Good. Okay, so let's see. So far I've got this. Negative 1, I'm already off the paper. Let's go this way then. How about 2? 2 squared is 4. Minus 6 times 2. 4 minus 12? Negative 8 plus 5? That 3? I hope I'm doing it right. You know, sometimes you do these in your head. No, that's not right. It's 4 minus 12 is negative 8. Negative 8 plus 5 is negative, right? And so now I do my next one here is 2, 1, 2. Okay, this is table of values. So I'm not going to continue, but I just want you to get the idea. This can be helpful if the other method's not working, you want a few extra points. This will work with any function. You can always set up a table of values. If you don't know an x value, plug it in, you get a y value. Okay, just remember this is always there for you. Now let's review using the table of value method. So this is what's on the bottom of your page here. First you say, what's A, what's B, what's C? A is 1, B is, C is, concave up or down? Because A is positive, so I know it's going to be, you know, a smile. What's the y-intercept? And see this little note here, what does that mean? That's a 0. That notation telling us. What's it telling us? Yes? Yes. This says, here's what x's value is. Plug it in, you get 5. All right. Axis of symmetry. X equals negative b up to 2a. It's a line, so x equals is important. That says I'm defining a line. So x equals negative b. Well, negative 6. 6 over 2 times a. That's 3. X equals 3. And we graph that. That is the graph of the vertical line that goes through all the points on the graph that have an x value of 3. And that's our guideline. It's our axis of symmetry, our symmetry line. We know what that is. We can hold on that. We just did a whole big thing on symmetry. Now to find the vertex, look at this. What is this telling me? What? It's telling me the coordinates, right? What's the x coordinate? Yeah, it's negative b over 2a, which I just figured out. Why is it? Because it always lives on the axis of symmetry. That's where your turning point's going to be, on that gold line. Now what does this mean? F of negative b over 2a. Right? Yeah. That means f of 3. And that means when x is 3, what do you get? Well, I don't know. 3 squared is 9. 9 minus 6 times 3. 9 minus 18 is negative 9. Negative 9 plus 5. Negative 4. All right, so I got the vertex. 1, 2, 3. 1, 2, 3, 4. Concave up, right? How many zeros will this have? 2. How do you know? How do you know? zeros are where it intercepts the x-axis. I can see it's going to be twice. There was another way we learned about. Remember what this thing is called? This is called it is in the quadratic formula. It's the thing under the radical, right?
Yeah.
It's called the discriminant. And we can use this to test how many real zeros we're going to have. So you plug in b squared minus 4ac. So what is b squared? Positive, correct? Negative times negative. Minus 4 times a times c. So that's 36 minus 20 equals 16. Now what this tells you is that when you're doing your quadratic formula, there's a positive number under here. Can I take the square root of any positive number? Sure. I may not get the exact value, and I'm going to add it, and I'm going to subtract it. So how many zeros will I find? 2 of them. What if your discriminant is 0? Right? The square root of 0 is 0. You're adding and subtracting 0. You're only going to have 1. So if your discriminant equals 0, there is 1 real 0. And if you have a less than 0, it means there's a negative number under here. In the real number system, can we take the square root of the negative? No. And that is when there are no real solutions. Now again, I keep saying this word real, or no real zeros. Why do I say the word real? Why am I qualifying that? Anybody know? Why am I using this word? Because you will learn, here's our real number system, right? In our real number system, we have rational numbers, and we have irrational numbers. And, you know, they teach this in Math 8. Anybody here take Math 8? No. Okay, so it's good to know. So rational numbers are all the numbers we can write as fractions, and irrational numbers are numbers we can't write as fractions. You mean there's numbers we can't write as fractions? You're familiar with pi, right? Well, if somebody recite pi, I'm glad I have one student who could do it to like several hundred digits, not here luckily. 3.1415, right? We could go on for how long? Forever. There is no pattern that anybody has ever found in pi. It never stops. You cannot write it as a fraction. So it's here. Things like square root 2. Also, same thing is true of any square root that is not of a perfect square. These are irrational numbers. So we have those. We got all kinds of things, integers and whole numbers. You know, those are all rational. So there's also something called complex. Yeah. So there's real numbers are under complex, but they also have something called imaginary numbers. Yes, we do. And you can take square roots of negatives here, but we can't do it here. So again, in Algebra 2, you're going to learn more about these things and how to find all the zeros, even if there aren't any real ones. There can be some imaginary ones. So again, just kind of setting up with the language a little bit. But anyway, there are 2 of them, right? There are going to be 2 of these. Oh, I forgot to do my y-intercept. 1, 2, 3. I just want to graph my y-intercept. Because I know this is a line of symmetry. 1, 2, 3. 1, 2, 3. Right? There's going to be one on the other side. Again, I'm just looking for little guide points. And now we have to find our zeros. And you do that by setting your function equal to 0. And then how do I find the zeros? We've been practicing this. How do I do it? A couple of ways, right? Let's do factoring. If it's factorable, sometimes this is the fastest way. Are there 2 numbers that multiply to positive 5 that add to negative 6? Yes, sir? Negative 5 and negative 1. Does that work? It does. So then what are the zeros? 5 and 1? Okay. Is that right? Yes, okay. So 5 and 1. So there's 1 here. That's 1, 2, 3, 4, 5. And it should be symmetric, and it is. And now I can sketch through it. And that's factoring. Okay, factoring method. And I believe that next slide is find it by factoring, which we just did that, right? Zeros are found when f of x equals 0, and we just did that. So let's review quadratic formula as a method for finding zeros. So there's the quadratic formula, and I should put an x equals here, because this is the solution to the equation ax squared plus bx plus c equals 0. What x's make this true? X equals that. So if I want to use the quadratic formula, why is this one different than the one on the paper? I'm going to go back and putting it to what it was, x squared minus 6x plus b. I don't So, A equals 1, B equals -6, C equals 8. So x equals negative b, negative 6, plus or minus square root of b squared minus 4ac. Did we do that already? B squared minus 4ac is 36 minus 4 times 1 times a is 32. So it's 4, all over 2a. So 6 plus or minus 2 over 2. 6, well, actually I can reduce that, right? That's 3 plus or minus 1. 3 minus 1 is 2. 3 plus 1 is 4. Why are these all different? I don't know, I'm confused. Did I confuse myself here? Is this different than the one on your paper? Yes. Okay, that's why. All right, never mind. Yeah, that would be the one on our paper. Sorry, let's see. I have that one someplace here. Wow. Sorry, friends. Sorry. I gave up. This one is a. Did I mess you up? Yes. X equals. What? All right, let's get this together here. That's a big whoops. I don't know why it's doing that. Okay, so then it's up here. We got our vertex. I've got to figure that out again. 9 minus 18, negative 9 plus 8. Negative 9 plus 8, negative 1?
Yes.
Yeah, I did that. I don't know why they had the wrong one in there. 3, negative 1. We still have 2 of these things. We found them already. Yes. Teacher of the year one. All right, so I'm just redoing the factoring just to make sure I'm doing it right. Oh, it could have been worse. Okay, so let's see. This one is now 4 and 2. So x is 2 and 4. The factoring method. And we just did, believe it or not, we did this with the quadratic formula. 6 plus or minus came out to square root 4 over 2. Right, we also got 6 plus or minus 2 over 2. 3 plus or minus 1, 2, and 4. All right, catching myself up here. Quadratic formula. Completing the square. All right, we can do. Let me go to the real page for completing the square. Go to page 9. Completing the square. Okay, so remember that now. You say x squared minus 6x plus 8 equals 0. So completing the square, you want this guy on that side. X squared minus 6x, leave a space, equals negative 8. Half it, square it. So it's half of negative 6, negative 3, and square that, plus 9. You added 9 to this side, add 9 to that side. Right, factor this, but it is a perfect square trinomial. Two numbers that, multiply to 9 and add to negative 6 is negative 3 twice, equals negative 8 plus 9. This is the square root of both sides, but we remember to take the negative root along with the positive root. All right, so x equals 3 plus or minus 1. We're back to where we were here, so we get 2 or 4. So again, sorry about that, my friends. So these are the 3 different typical ways of finding them. Yes, you can do it on the calculator as well, but this just gives you a little bit of a feel for how that works. And I will stop for a second here. I apologize for that mix-up. Are there questions? Because I went through this crazy fast here. Questions on that? Yes, sir. Vertex, how do you get the vertex? You can find negative d over 2a, which you do here. That's your x. What does f of that mean? You take f of that. What does that mean? It means your x is now 3, so you plug 3 in for these numbers and you make that calculation. Yeah? Anything else? We will find a new way for finding vertex. Will be easy soon. Yes? Yes, you don't have to do all 3. You only have to do 1. So I just wanted to demonstrate the 3 ways. Sometimes you cannot factor it. They are not factorable, in which case you have to use one of these. Use completing the square if there's a 1 in front of here, and this is an even number. Completing the square is then easy. Otherwise, it can be a little hard. Use the quadratic formula. So you can always use the quadratic formula. It will always work. All righty. That's what we know. That's what you learned last year. And now we're going to learn a new way, because the vertex is always one of those things that we have trouble finding. Isn't it? I can't remember how to do the vertex. So we're going to learn another way to find the vertex of a parabola. Yay, on the back. So this is new. This is algebra 2. So we're going to rewrite the standard form of a parabola into the vertex form of a parabola, and that's this. Y equals a times x minus h squared plus k. Anything familiar with this? Where have we seen this before? Yeah.
Isn't that like the same thing as circle?
Circle. Remember circle equations? We had x minus h squared plus y minus k squared equals r squared, right? Circle, and see this? So any of these conic sections, you will start seeing a lot of this hk stuff repeating over and over. This is circle, this is parabola, there's different ones for ellipses and hyperbolas. So you'll be seeing that again. That's what they have in common there. And it's very similar. HK, it's kind of sort of a little bit like the center of a parabola, but we're talking about the vertex. H comma K is the vertex of that parabola. It is. The thing you have to be careful of is that this is a subtraction, but this is an addition. So if you're pulling out a vertex, you have to kind of interpret it. So let's review. Let's learn how to do this. Here is standard form. I want to put it in this form because let me just give you an example. If I have in vertex form y equals x minus 2 squared plus 5, what's the vertex? 2 comma 5. H and K. You can just say, here it is. Now, I don't have to do x equals negative b over 2a. I don't have to do any of that stuff. Vertex right there. In fact, what is the axis of symmetry given this equation? Yeah, x equals 2. So it's way easier to do this when you're in vertex form. So watch how to do it. Let's see. I'm trying to look at the little notes here. Just ignore the notes for a second. And just watch what we're doing here. You have to know how to complete the square. You have to know how to complete the square. So if I have y equals x squared minus 6x plus 8. Now I'm going to rewrite it. However, I'm leaving this little space here. Leaving a little space. I'm going to complete the square on this. So what is half of this and then square it? 9, right? So it's negative 3 squared is 9. Now I'm on the same side of the equal, and I added 9. What can I do to keep this thing equivalent? I could add 9 to the other side. Well, can't I just subtract 9 right here? What did I do? I added 9 and I subtracted 9. That's the net of adding 0. Did I really change the value of this? No. Now I can write this as my perfect square. And what is 8 minus 9? And this is now in vertex form. What's the vertex? Well, remember x minus h squared plus k. So h is 3. Now plus k is negative 1, so negative 1. Vertex, no fuss, no muss. What's the axis of symmetry? X equals 3. I can go get it that way. What? Do we follow that? Sort of? Now the one on your paper, no, this is not even on there. I don't know. I am going to see if that's here. I don't think it is. Okay. We're going to kind of leave the notes for a second here. We're going to follow what I have here. For some reason, this slide got lost. If you have a little blank piece of paper, or if you want to use the back of your warm-up, we're going to actually do these ones as examples, okay? So we're going to do these ones as examples. We lost a flip someplace, so we have a new one. All right. So what are the steps? The steps are, you're going to be completing the square. So the first thing you do is you write these terms with an x in them, leave a space, and just put the plus 26 on the side. Yeah, everybody has a place to write. Okay, we'll move it to the side. We're going to complete the square. So half it, square it. Half of 8. Half of 8? Square that. Now, if I add 16 here, somewhere along the line, I got to subtract 16. Don't forget to do that because you need to be writing this down, my friends. You do. We are going to actually have summatives on this. You need to write this down. Okay. And so now I'm going to take this thing and write it as its binomial square. And then what is 26 minus 16? 10? So I am in vertex form. What's the vertex? Careful, it's x minus. Yeah, then you got to be careful with that negative. It's going to get you every time. So what is the x value? Negative 4. What's the y value? 10. What's the axis of symmetry? X equals -4. Okay. Let's try this. Questions, right? All right, let's try this guy over here. So y equals, you just kind of rewrite x squared plus 4x. Now leave a little space here for that -4. Let's put it on the side. Complete the square here. What's half of 4? Square it. Plus 4. Just added 4. I better subtract 4. I'm just putting it over here. Net add is 0. Then I'm going to write this as its square. -4 minus 4? -8. So then, what is the vertex? And -8. So this one, right, it's the opposite. It's like what goes in here to make the 0? Maybe that'll help you remember what to do here. And then -8 just like that. So what's my axis of symmetry? X equals, don't forget X equals because it's a line. You're writing the equation of a line when you write the axis of symmetry. Yeah. How am I getting it? You're basically factoring this. What two numbers multiply to 4 but add to 2? 2 and 2. It will always be the same number. That's what completing the square does for us. Alrighty. Now this one's a little more complicated when you have a number up front here. So here's what you do. Watch carefully. I'm just going to factor out the 2 from the first two terms only. So I put the 2 here, and what am I left with? X squared minus 4x. Leave a space, close the parenthesis, and my plus 10 is just sitting here. So far I haven't really changed anything yet, have I? I just factored out from the x variables and shoved this over to the side. Complete the square in here. So -4. So you take half of that and square it. Half of -4 is -2, plus 4, right? Now let's think about what I really just added to the equation. 8. Why 8? See this plus 4? But it's 2 times that. 2 times 4 is 8. So what do I need to subtract to make this equivalent? 8. Do we see that? Yeah. Okay. Now I want to turn this into its square. X minus 2 squared plus 10 minus 8 plus 2. There I am. I'm in vertex form because there can be an A up front here. Here it is. There's a constant up front. Now we're going to learn more about what this constant does next class. So what is the vertex? 2, 2. And what's the axis of symmetry? X equals 2. Who followed? X equals 2. Why did I write an 8? I have no idea. Yeah? Okay, let's try another one. These are a little bit trickier. So y equals, now this is a negative. Okay. So factor out the negative. You basically want this to just be 1x squared inside here. You always divide by whatever that is. So x squared, ooh, so -12x divided by -3 is plus 4x, isn't it? Okay, leave a little space. Here's my -8. I do this just still here. Whew. All right, complete the square. Half it, square it. Plus, what goes here? 4. Half of 4 is 2. 2 squared is 4. Now let's think about what we just did here. Did I add 4? What did I do? -3 times 4 is -12. So what goes here? Plus 12. What? Has to be opposite. I really subtracted 12. Huh. So now you got to add it back to get the 0. Yes, sir.
If you didn't put half of the square, then you get the same thing.
Huh? As what?
You know when you see an x squared plus 4x, and then you half the 4x, and then you square it,
Yeah.
to 4.
Yeah.
If you just cut that out, if you didn't add the 12, wouldn't it be the same answer?
I'm lost.
If you never put the 4 in.
I have to put the 4 in though. Why do I have to put the 4 in? I have to. Because I want it to look like this. Because now what's the next step? I need it to look like this. That's why I'm doing this. Right? I'm not sure I understand your question. But the reason I'm doing all this is because I want it to look like y equals 8 times x minus 8 squared plus 8. Now it does. What's my vertex? And what's the axis of symmetry? Okay, and I'm not sure I understand your question, Mason. So I obviously did not answer it since I didn't understand it. But we're doing all this stuff here, not because I'm trying to get back here, I'm trying to get to another form of it. Negatives can be a little tricky, so here's some negatives. So it's actually the same thing. Pretend it's a -1, right? You take it out. What's left here? I get an x squared plus 6x. Leave a space and there's nothing to add. Okay. Right? It's kind of like a plus 0. Half this, square it. What do you get? 9. Half of 6 is 3. 3 squared is 9. Now let's see what I have to do to keep this thing in balance. It's really a -9, isn't it? So what do I have to do? Plus 9. I am not adding 9 twice. There's a negative in front. This is a -9. Plus 9, that's 0. So this becomes negative x plus 3 squared plus 9. What's the vertex? -3, 9, and x equals -3 is the axis of symmetry. Is anybody like, what? Huh? What? What? Yes?
So is the negative, does it like not really matter then?
It will matter later. It will matter next class. So for right now, we're just worrying about vertex. We're going to work with this stuff. It's cool stuff. Yes?
Did you write like -1 instead of just negative?
You want to put a 1 here?
Yeah.
You could, but then it's not in simplest form.
Okay.
So we always just want to keep it in simplest form if we can. Let's try this guy. So same thing. There's a negative up front. You take it out. So now what happens? That flips your signs. Leave a little space here. This time I do have this little -2 kind of hanging out. All right, so I haven't really done anything yet, but now I want to complete the square here. I have a 2. Take half of 2. That's 1. 1 squared plus 1. Did I really add 1? What did I really do? -1. So how do I keep this in balance? Plus 1. Hi. So you got to be really careful with that. Oh, really? See, it's a -1. That's add 1. So y equals negative x plus 1 squared, right? That's this. What's -2 plus 1? -1? So now I got to figure out, what is my vertex? -1. -1. Because remember, this is, it's a plus k. So it's -h plus k. So -h, that has to be a -1 plus k. You added -1. And then my axis of symmetry. Whoa. -1. Question? No, just start that. That's okay. Yes, sir, Lena.
For the fourth one,
This one?
yeah, you did -3. Wait,
Yes.
never mind.
Yeah, and you gotta be so careful with these at first. Whoa, it takes a little doing before these become automatic, right? Yeah, oh, we gotta think about it. What's this? All right, so now, when we're graphing, this, we can return to your notes now. I don't know what happened to the top half here. You can actually do those for fun if you wanted to, because fun is fun. But, if I want to graph it now, so, same kind of thing, I still need, A, B, C. And then, so is it concave up or down? Now, axis of symmetry and vertex, I'm going to do it a little differently now. I'm going to convert this to that form. So I factor out the 3 for the first 2 terms, right? And then I do, okay, half of this and square it, that's plus 4. But now I have to balance it. 3 times 4, that's really 12. So I subtract 12. And now I've got 3 times x plus 2 squared minus 4. What's my vertex? I'm going to do that one next. What's my vertex? You think about what would go in here to make this 0, and then just take this as it is. What's my axis of symmetry? Okay, so I'm using this method now to find those 2 things. Everything else you kind of do the same, find your zeros, right? Everything will be the same otherwise, and then you can graph it. Questions? Questions? That's slightly different on your paper. It does ask for vertex form, and I did that down here. Right, your paper has that as the first thing. I don't know why these don't match, but they don't. Okay. What do you think? I'm going to turn another one into vertex form just to do it. And then I will give you that homework paper that you can do here. So negative x squared plus 2x, right? Because I took out the negative, and there's the plus 3. Half x squared, that's a plus 1. But there's a negative up front. I'm really subtracting 1, so I have to add 1. And this becomes negative x plus 1 squared plus 4. That's vertex form. So what's my vertex? Good here, be careful. What's the vertex? Ethan? Good. So what's the axis of symmetry? X equals negative 1, a line, right? So I will mark you wrong. There's no x equal. You didn't give me the axis of symmetry. And then you proceed as we did before. Instead of hunting down, right? You can do everything you did before. Questions? We're just done to pass. Okay. You can finish these if you like. I'm going to give you a worksheet. You can work on that in class.